Hi everyone, welcome back. In this segment, we're going to be talking about phasors, which is one of the harder topics in 16B. So, in the previous section, we have seen that if we try to solve differential equations for all sorts of circuits, once we add in different components like capacitors and inductors, the differential equations, it soon becomes too complicated for us to solve. In a reasonable amount of time. So to deal with that, for a specific type of input, we devised a scheme called phasors. Okay, so if the input is sinusoidal, that is, if the input can be written in the form of Vt being equal to V0 times cosine of omega t plus phi. Okay, if it's a sine wave, same thing. We just turn it into a cosine wave by saying that sine of x is equal to cosine of pi over 2 minus x. Okay? All right. So for this type of input, we can turn it into a linear equation. And the next 20 minutes, it's about how we're going to do it. Okay? So from question 1 on the same worksheet, the last problem, part F, we know that cosine of x is equal to 1/2 times e to the jx plus e to the negative jx. And so we have Vt being equal to V0 over 2 times e to the j omega t plus phi plus V0 over 2 times e to the negative j omega t plus phi. And so that is equal to V0 over 2 times e to the j phi times e to the j omega t plus V0 over 2 times e to the negative j phi times e to the negative j omega t. Okay, we now let this term be the phasor representation of the original input V. So we say that V is equal to V0 over 2 times e to the j phi. Okay, so this is a definition. We define this as the phasor representation of the same input. And then we put it back to see that the original V of t is equal to V tilde times e to the j omega t, because we notice that this is exactly the conjugate of V tilde. So this is just V tilde's conjugate times e to the negative j omega t. Okay? So observe that so we have this transformation between sinusoidal inputs. We convert a sinusoidal input into its phasor representation. And now with this equation right here, we can turn a phasor representation of the sinusoidal input back into the original form. Am I right? Okay. So phasors has a number of properties. So the first property of phasors is that it is unique. Okay? So if I have two inputs on the same frequency, I'd like to reiterate that. So they have to be on the same frequency. That is omega. With the same phasor representation. Then V1, the original two inputs, are the same. The reason why this is true is that we just apply the formula that we just wrote above. Vt is equal to V tilde times e to j omega t plus the conjugate of V tilde times e to the negative j omega t. Okay. Since they're on the same frequency, the original inputs must be the same. Okay. obviously these two inputs, they have to be on the same frequency for this to properly work. All right, after the second property, we have linearity. So if we have V1 and V2, again, they have to be on the same frequency. That is omega. Then AV1 and BV2 must be also sinusoidal with the same frequency. It corresponds to some phasor representation on the same frequency, right? We claim that this is equal, its phasor representation is equal to A times V1 tilde plus B times V2 tilde, okay? So phasors are actually linear, okay? So again, we apply the same formula to see that AV1 plus BV2 is equal to V1 times e to the j omega t. I mean, there's A in the front, plus V1 tilde conjugate times e to the negative j omega t. We add it with B times V2 tilde times e to the j omega t plus the conjugate of V2 tilde times e to the negative j omega t. And that is equal to A V1 tilde plus B V2 tilde times e to the j omega t plus A, the conjugate of V1 tilde, plus B, the conjugate of V2 tilde, times e to the negative j omega t. Okay? So sum of conjugates is the conjugate of the sum. And so we see, so we don't need to write another equation, but rather we note that this thing, this expression, is exactly the same, is exactly the conjugate of A V1 tilde plus B V2 tilde. Okay? And so the phasor representation of AV1 plus BV2 would then just be A V1 tilde plus B V2 tilde, and phasors are linear. All right. So the third property that we're interested in is how do we take differentiation? How do we take the derivatives in phasor representation? So when we differentiate a variable, so let's say that V is an input on some frequency omega. Okay. Then we claim that dV dt, I mean, it must also be on the same frequency. It corresponds to some phasor representation, and its phasor representation, we claim it's j omega times V tilde, which is the phasor representation of the input itself. So to see that this is true, we just write out V in terms of V tilde. So V of t is equal to V tilde times e to j omega t plus the conjugate of V tilde times e to the negative j omega t. So if we take the derivative dV dt over time, this is V tilde. V tilde is defined as V0 times e to j phi. So that's a constant that has nothing to do with the time. It's constant. So just leave it. And then the derivative of e to j omega t, just copy over the coefficients and take the derivative, just using the chain rule right here. For the other part, we do the same thing. The conjugate of v tilde times negative j omega times e to the negative j omega t. Okay, so negative j omega, we know that it's the conjugate of j omega, and a product of conjugates might be a little bit counterintuitive, but the product of conjugates is actually the conjugate of the product. Okay, so this is actually equal to v j omega, actually j omega v tilde times e to the j omega t plus the conjugate of j omega v tilde times e to the negative j omega t. Okay, and so its phasor representation, the phasor representation of the derivative is simply j omega v tilde. Okay, so there are a couple of things to note about phasors. So although I've been using V's as my example when I'm explaining phasors, phasors does not restrict to voltages. It could be the current, could be any physical quantity that you're interested in studying. As long as it's sinusoidal, you can pull the same stuff. Okay. And second thing, be especially careful when you're using phasors. Everything must be on the same frequency in order to use phasor properly. There are two things on different frequencies. It'll be a little bit more complicated. Okay. So now, as we went over the different properties of phasors, let's take a look at question number 2 on the worksheet. So it says right here that the phasor representation contains the magnitude V0 and the phase of the signal. So if the signal is actually V of t, that equals V0 times cosine of omega t plus 5V, then V0 is just the magnitude of the signal and 5V is just the phase. Okay, just some technical terms. All right. So, as always, if you want to take a couple of minutes to think about these questions, given the properties that we have just discussed, just pause the video for like a couple of minutes and 3, 2, 1, unpause. So in this question, we define the impedance of a circuit component to be the ratio between the phasor voltage and the phasor current. Remember when we talked about the fact that you can actually do phasor current as well as phasor voltage equally well. I mean, as long as they're on the same frequency, as long as all the components they're on the same frequency, you can do phasor anywhere. Okay. So in this question, we want to derive the impedances of resistors, capacitors, and inductors, which will extend Ohm's law and reveal a common method of phasor domain analysis for all three circuit components. Okay. So we want to consider a resistor circuit below with a sinusoidal current. So the intuition is that we can just simply represent it in phasor domain. We want to find the impedance of this resistor, ZR. So we know that in the physical domain, without phasors, we have V, the voltage across the resistor, being equal to I times R. So I'm using lowercase letters to indicate things in the physical domain, and I'm using uppercase letters with tildes on top to indicate things in the phasor domain. Okay. So now, to find the impedance of the resistor, we just take the phasor domain of both sides. As we explained, we take the phasor of both sides. The two quantities, if they're equal, the phasor domain is also going to be equal. The phasor representation is also going to be equal. So if we take the phasor representation of both sides, V tilde is equal to the phasor representation of IR. R is a constant that we know. So since phasors are linear, as we explained, the phasor representation of IR is just R times the phasor representation of I, which is just the phasor current. And so the impedance of the resistor is just, by definition, V tilde over I tilde, which is, again, R. So we still have Ohm's law in a sense. Okay. All right. So for part B, we want to consider a capacitor circuit below with a sinusoidal voltage. Again, it is something we can express in phasor domain. So We know that a capacitor, it follows the IV, it has the IV characteristics of I equals C dV dt. So again, we take the phasor of both sides to see that the phasor current is equal to the phasor representation of C times dV dt. So again, since C is a constant, and since phasors are linear, we see that this is equal to C times the phasor representation of dV dt. Okay, so as we explained in the differentiations part, the phasor representation of a derivative is just C times J omega V tilde. Okay, and so we see that the impedance of a capacitor is equal to VC tilde, V tilde over I tilde. By moving terms around, we see that this is just 1 over J omega C. Okay, as you can see, by simply using the properties that we just derived a little while ago, these problems are relatively easy to solve. All right, so since you have an example of how you can derive the impedance of a capacitor, you can try and pause the video to think for like a minute how you can derive the impedance of an inductor. All right. Now we're going to derive the impedance of an inductor together. So an inductor, as we have explained earlier, is a component with the IV characteristics of V equals L di dt. Okay. And if we take the phasor representation of both sides, we see that V tilde is equal to the phasor representation of L times di dt. Again, since L is constant and phasors are linear, we see that this is equal to L times the phasor representation of di dt, which we know by the third property we derived is equal to L times J omega I tilde. And so the impedance of the inductor is equal to V tilde over I tilde, which is equal to J omega L. So these questions looks a little bit intimidating, but after all, if you actually think about these, it wouldn't be too hard. Like using the properties that we just derived, don't be intimidated, wouldn't be too hard. All right, so what's the point of having these impedances? Doesn't make any sense. How would you have impedance that is a complex number? Let's be on the point. Let's be on the point. The really interesting thing is all of these components, whether it be linear or nonlinear, has a constant impedance, meaning it follows some sort of an Ohm's law in phasor domain. And what's really interesting is that phasors are linear, which means that KCL and KVL are preserved in phasor domain in their full entirety. So that means we can turn things, if the input is sinusoidal, we can turn things into phasor domain, solve it as if it were a resistor circuit, find the phasor voltage, V out tilde, for instance, and then turn it back into the regular domain using the formula we just derived, namely V, the t, equals V tilde e to j omega t plus the conjugate of V tilde times e to a negative j omega t. We can just turn it back into the regular domain. But this is what is really interesting about phasors. We don't need to solve for differential equations anymore. And we'll see that in a second. That concludes our walkthrough for question number 2 on the worksheet.